always, with our roundtables, do want to acknowledge that for me, coming from UW Tacoma, and I'm joining from the ancestral land of the Coast Salish people, and particularly the Puyallup tribe of Indians. And as with all roundtables, encourage folks to think about how Indigenous knowledge and leadership play into the work that you are doing around a particular topic, or the connections and collaborations that may exist there. But with that, as folks continue to join, I'm going to hand things over to Sarah. Very excited for today's conversation and this intersection between marine energy as well as kind of the impact on the benthic side, which I know many of us in the Salish Sea community of roundtables are particularly interested in those critters. So with that, all yours, Sarah.
Thank you, Marielle. And thank you to all of you who are joining today. It's a large group, and so I'm sure there is a wide range of knowledge base that you all have come in with. And so I hope that each of you finds something interesting in my presentation, something new. It is going to be kind of a high-level overview of the types of ocean renewables that we are looking at in the Pacific Northwest, with a focus then on how we've been assessing the benthic, various kinds of benthic impacts. When Marielle sends out the slides and the link to the recording after, I'm also going to send her a link of links of other presentations that I or other members of the PMEC or the POWC team have given, some that focus on seabirds, some that focus on secondary entanglement, one that I've done on EMF. And so if you want to take a deeper dive into any of the other issues, we'll share those resources with you. But now I will share the presentation I've prepared today. Okay, so my name is Dr. Sarah Henkel. I am based at the Hatfield Marine Science Center, which is in Newport, Oregon. It's Oregon State University's Marine Lab. I am right now I've been an associate director and right now the acting director of the Pacific Marine Energy Center, which is a 3-university consortium focused on marine renewable energy. At Oregon State University, we've mostly focused on wave energy because we have great wave resources off Oregon. The University of Washington has mostly focused on tidal energy applications, and the University of Alaska Fairbanks focus on tidal and in-stream river energy. So I'll start with why are we looking at offshore renewables? So as these maps indicate, much of the US is concentrated on the coasts, and there are strong wind and wave resources on the West Coast and in the Northeast, where we have big load centers. When we talk about ocean renewables, over the years we've used many, many terms. Are they marine renewable energy, ocean renewable energy, offshore renewable energy? We've got tidal energy, current energy. Like I mentioned, those have been mostly what's been happening at UW and University of Alaska Fairbanks. OTEC is ocean thermal energy conversion, which I'm not going to touch on today because you need warm water for that to work. Not something, we don't have warm surface waters up here. Wave energy and offshore wind. And these first 4 we refer to as MHK or marine hydrokinetics because they all operated by the movement of the water, the hydrokinetics themselves. Whereas offshore wind is deployed in the ocean, but isn't actually considered a marine energy because it's not the water that's making the energy. So I'm going to give a few slides about offshore wind and then transition into the marine hydrokinetics. So there were some earlier West Coast floating wind proposed pilot projects. A lot of wind in the news in the last couple of years and some statements of rushing into it. But I just want to make people aware that the WindFloat Pacific project was a project proposed back in 2013. for 5 turbines off Coos Bay, Oregon, to demonstrate the potential of deep water floating wind. And in a little bit, I'll get into some of the work that we did related to that. And in 2016, there was a proposed project off Morro Bay, or California, of 100 floating offshore turbines. And so this is something that in the research community, we have been thinking about and working towards for a long time. You may be familiar with the Oregon process. So initially they had call areas released back in 2022. And those were really big areas that really stressed a lot of people out because they were so large. But the call process in the BOEM process is a really like, okay, we're going to put these areas out here and we are calling for information. What do people know about habitats here? What do they know about existing uses? Tell us everything about these areas in the ocean. So after that call process, then they released draft wind energy areas, which you can see in the middle panel, that are much smaller. And so if you're familiar with off Oregon, that Coos Bay call area got a lot smaller because of some Navy activity in the area and some existing NOAA surveys that happen in those areas. And so they really reduced the potential draft wind energy area. And then when they were preparing for the lease auctions, the areas, in fact, got a little bit smaller still. That auction was planned for October 2024. It was postponed, and it's not likely to happen anytime in the next 4 years or maybe thereafter. Now, California did complete its leasing process prior to the change in administration. And so there are 5 leaseholders across the 2 California areas, 2 leaseholders off Eureka and 3 leaseholders off Morro Bay. And the timeline for those projects has been slowing down quite a bit as the federal landscape has been changing. In terms of hydrokinetic ocean renewables, Marielle asked me if I had a favorite. I'm not going to say one, but the hydrokinetics have some really huge advantages over offshore wind or even onshore wind or solar. And for these 3 main reasons. So water is 1,000 times more dense than air. And so you can get a lot more power with the flow of the water versus flow of air. It's also available 24/7. The waves and the tides, they never stop. Now there is variability. Sometimes the tides have a greater tidal range, and so there's faster moving water and more power, and sometimes less. But as you know, you can look up those tide tables for decades in the future, so they're very predictable. The waves, there's going to be times of stronger waves and lesser waves, but they're never off. And with the NOAA buoys that we have out there, we have extremely good predictions about 48 hours out. And so the constant availability and the predictability, which can help the utilities manage their portfolio of energy resources, makes them really attractive. Within the hydrokinetic, I'll talk a little bit about tidal and then mostly about wave, because that's what Oregon State's been working on. So when we think about harnessing tidal resources, there's 2 main ways that this has been done over the years. Historically, there have been a few installations of tidal barrages, and I have a little red bullet point next to this one because this is not a really attractive option. Think of it really as like a marine hydropower dam. And so at high tide, the water would flow into the bay. They close the gates of the barrage and let the tide go out on the ocean side so that there's a really big differential between the bay and the ocean side. And then at low tide, they will open the gates and let the tide run out of the bay all at once really fast and turn the turbines. You can imagine maybe some potential environmental changes that might be associated with changing the timing of the tidal exchange so dramatically. And also you lose that constantness, which is the advantage of marine hydrokinetics, because you're only turning the turbines when you're opening those doors of the barrage. Since that time, industry has moved forward and has been developing a number of underwater tidal turbines that we kind of think of as like underwater wind, because the turbines, the technology of the turbines is really similar. And so we can put these turbines in the narrow areas and use the constantly flowing tides to generate power. One of the longest running demonstrations of this was in the East Coast in New York's East River. Way back in 2002, they installed 2 turbines that you can see there in the photographs. From 2006 to 2010, they put 6 full-scale turbines and connected them to the grid. And then from 2013 to 2021, they upgraded various components. They did a bunch of environmental monitoring studies. Over 312 megawatts of tidal power was delivered to the grid, but it was always a demonstration project. And in 2021, it was completely decommissioned. And we do not have any installed tidal power in the US at the moment, beyond a few demonstrations in the Salish Sea and in Alaska. So on the West Coast, there are a few estuaries that have really strong tidal exchanges and some nice narrow areas in which we could install these turbines. In California, we're looking at San Francisco Bay, great tidal resource. You can imagine, though, that there are maybe a lot of issues with putting turbines in the entrance to San Francisco Bay. So we'll see if we ever overcome those hurdles. Salish Sea, good amount of resource there. And then Cook Inlet, huge potential in Cook Inlet in Alaska. In the Salish Sea, back in 2015, there was a proposed demonstration product with the Snohomish PUD, and currently there's what we call the Opalco project. So the Snohomish PUD project ultimately failed due to the cost. That was a long time ago. It was the first of its kind technology. A lot of questions about survivability, a lot of questions about potential environmental impact, some tribal opposition, and some telecom cable litigation. So just a whole series of issues that sort of made it intractable. But currently, there is a single ORPC, that's Ocean Renewable Power Company turbine, deployed in the Salish Sea. It's been funded still, so far as we know, funded through the bipartisan infrastructure law funds, and one of 2 projects that will be chosen later this year to continue. The other is in Cook Inlet. This is a much more advanced technology. There's a better global knowledge base, as tidal has been installed and tested in a number of places around the world by now. And we've got better environmental monitoring tools. So we're really excited about this project, excited about the demonstration in Salish Sea and the potential for a really full-scale deployment in Cook Inlet that could really support a lot of communities in Alaska. Now, when it comes to wave, there's a much wider variety of waves to harness the wave resources than when we look at offshore wind or tidal energy, where the turbine technology has coalesced around 2 or 3 bladed turbines. And so on the top row here, I have a number of cartoons that demonstrate generally how the wave resources might be harnessed. And then at the bottom, some actual devices that have been deployed and tested over the years around the world. And I'll just highlight this one at the end. This ocean energy buoy was built in the shipyard in Portland. It was towed all the way over to Hawaii. It's currently being tested in Hawaii. And the plan was to tow it all the way back to Oregon to test it here. But it had some issues with being towed all the way across the Pacific Ocean in one direction. And so they're rethinking their plan of towing it all the way back. Now, there have been efforts to test, deploy, demonstrate wave energy in the Pacific, going back now, we've just hit over 20 years. So in 2004, the Wave Energy Test Site was established off the Marine Corps Base, Hawaii, and that is where that ocean energy device is currently deployed. Some of you may be aware that in 2007, there was a wave energy device by a company, Finnevera, deployed off Newport, Oregon. That same year, we held a workshop here at Hatfield looking at the ecological effects of wave energy development. And the following year, we established what is now called the Pacific Marine Energy Center. At the time, the US Department of Energy named it the Northwest National Marine Renewable Energy Center, which is an acronym that starts with NNM. So we worked with that for a while and then suggested to the Department of Energy that maybe we could just be PMEC and reduce the awkward pronunciation. Later that year, we did support Columbia Power Technologies in testing a small-scale device of theirs off Newport. In 2011, Aquamarine, which makes this device called the Oyster, leased some offices in Newport, Oregon, with the idea of deploying. It never happened. In 2012, we supported Columbia Power Technologies in deploying a 1/7 scale device off Newport. And then in 2014, WETS, the Wave Energy Site in Hawaii, added 2 more berths and have since deployed a number of devices. So it's been something that we in Oregon and Hawaii have been working towards for a really long time. The project that we're nearly have completed is our PacWave project. And so we started a feasibility study for this back in 2011. We officially started our license application in 2013. We submitted that in 2019, and we received the license in 2021. So an 8-year licensing process. We did start construction in 2021. We ended up not completing the construction until fall of 2024. So not too bad for such a long timeline that we're only a year behind. And the goal of PacWave is to be similar to what WETS is in Hawaii, whereas WETS is in a bay in Hawaii with smaller waves. So the concept is that devices might go to Hawaii first, test, and then come to Oregon, fully energetic, open ocean environment to look at their survivability and power production. And so down here at the bottom of this map is Waldport, Oregon. Newport would be at the top of this map. The site itself is 1 mile across and 2 miles long, with it would be 4 berths in there. So 4 different developers could test at once. We've got 4 cables that's what we just completed at the end of 2024, going from the coast out to the site. Think of them as 4 extension cords, very, very long, 12-mile long extension cords. out to the site. Different wave energy developers, like those pictured on that earlier slide, can bring their device, plug them into our giant extension cords. The power goes back to this facility that we have on land. Each developer would have their own garage at that facility where the power comes in. And then they could analyze the power coming off there. We, the operators of Packway at Oregon State University, can certify their device to be at a certain power level. And we are also the ones that are conducting all of the environmental surveys. So I think I'm going to pause for a minute and see if there are any outstanding questions about technologies. Okay, so Squim Bay. Yes, there have been some very small wave energy deployments in Squim Bay, wave energy, tidal energy, small scale devices that have been tested for short periods of time. So yes, that is correct. See if I can scroll up.
And I think the other was just primarily a clarification about the tidal energy turbine and if that was a proposal or already deployed.
So ORPC, the one in the Salish Sea, maybe that hasn't been deployed. I know ORPC does have one deployed in Alaska, in the Galena community. It's possible the Salish Sea one is still being permitted, and maybe the deployment would happen after the down select. All right, so it seems like those are the few technology questions. Okay, so yes, and the Igiagig. All right, and Amy has a question. A quick technology question before.
You should be able to unmute now.
Yeah, I did. Thank you. Yeah, thank you, Sarah. This is all really interesting and helpful. My question about these tidal turbines and, AKA underwater wind, they're proposed in the one Opalco's for Rosario Strait. It's proposed to not have any kind of protective cowlings, just have these large, 49-foot diameter blades, 2 of them underwater. And I guess the technology question is, why would a technology not have some kind of protection? I mean, there's so many things in the water in the Salish Sea, from kelp and endangered species to massive amounts of wood when we have really high tides and storms. And so I just see that would be like a bare minimum to actually have something that's functional and sustainable, but that's not part of the proposal. So I wondered if you have any information.
So our colleagues at the University of Alaska they're actively researching all sorts of debris diversion approaches. So what can you deploy upstream of the turbine to maybe divert debris before it gets to where the turbine would be? Much of the research suggests that many of the animals are not using the center of the tidal channel because the flow rates are so high. So the places that are most attractive for deploying the turbines for harvesting energy are less attractive for many of the organisms. Our colleagues at University of Washington and at PNNL, with those test deployments in Squim Bay, they have a lot of underwater footage of organisms approaching the turbines, fishes, sea lions, and they're not passive particles, right? The fish can avoid the turbines. The sea lions are certainly curious, but could swim up to the turbines, investigate them, swim away. Certainly, yes, of course, the southern resident killer whales use the strait. But again, most of the observations have been that the organisms prefer to use the fringes of the channel where the flow isn't so great, whereas the turbine seeks to be where the flow is the greatest. Okay, and noise. Okay, so the next part of my presentation is going to get into the environmental effects. So we'll move in to that if we're kind of through with the technology elements.
Good. Thanks, Sarah.
Sure. Okay, so what are some potential environmental effects? So this figure that I have is from this 2021 paper that's potential environmental effects of deep water floating offshore wind energy. The article was focused on wind, but many of the questions are the same regardless of the technology. But this was a good meta-analysis that synthesized 89 other articles. So just as a figure to look, we've got potential habitat alterations to the seafloor, which is what I'll mostly focus on as a benthic ecologist. There are also potential for EMF from cables, which could impact both water column and benthic species. Noise, as someone just mentioned, then potential water quality impacts from any sort of leakage of hydraulic fluids or anti-fouling paint. Here, the structural impediments, because this is a figure from a wind paper, are above the water, but the same would be true for wave or tidal or any sort of subsea structure that could be impediments to organisms. And then atmosphere and oceanographic dynamics, which would affect all organisms. But again, I'm going to focus on the benthos. As I mentioned in my introduction, we have a whole series of webinars that we've done for various groups that I'll share. But we have a seabird and collision potential webinar that we've done. We've done an EMF one. We have not, I think we've even done the secondary entanglement for whales one, but I'll be sure to get those out to Marielle to be shared with the group. So as a benthic ecologist, I'm going to focus on the benthos. So how might benthic alterations occur? So this paper, this 2019 paper, has a lot of these like really complicated diagrams that almost look like a circuit board to me, but is very comprehensive. And so if you're interested in following up on this, I suggest this paper. But they've separated these potential effects into what are the human activities, what sorts of then abiotic effects would there be from those human activities, and then how are there going to be changes to the biology based on either the fact that there's hard structures there or that the natural substrate has changed. So really complicated diagram that looks like a circuit board, or I can just show you this picture of an anchor that we deployed. And you can see if you put a large object in a sedimentary environment and have high energy flow, you're going to get scour around the anchor. You can see how this anchor has been undercut a little bit. So the finer grain sizes are going to be put in suspension and moved downstream. So you're going to get changes in distribution of grain sizes. One thing that we've noticed a lot is accumulation of shell hash around the anchors. And this isn't material that's grown on and then fallen off. This is, we're still not really sure exactly where it's coming from, but the physics of putting an object in a sedimentary environment in flow is somehow entraining this shell hash material. You can see that the anchor itself has some worms, tube worms accumulated on it. So we've got that growth on artificial substrate. So there are a number of ways that benthic alterations can occur. So how do we survey the benthos? A number of ways. So we've got sonar surveys, and that can help us look at the physical characteristics of the seafloor. We might use remotely operated vehicles. We might drop a video lander down, use a video sled. And then if we want to make collections, I use a box core. There are a number of different types of grabs. So grab a big box of seafloor sediment, sieve it out, retain the organisms, and then back in the lab, we sort the organisms out to characterize what species are where, what types of sediment are they associated with. So we first started back in 2010, a project for BOEM, where we looked at a number of different sites that had been potentially targeted for, identified as targets for wave energy, and sampled them using a number of these methods. We used high resolution multi-beam sonar, we used acoustic backscatter, we used box core grabs, we did some video images of the seafloor, and characterized the seafloor sediment and organisms at these 8 sites, and then interpolated in between what we might expect the organisms to be. Then paper came out the following year, but of course the work was much later. Took some EPA data, some data that had been collected by the EPA, all the way from Southern California, all the way up to Vancouver Island, and did an analysis looking at how they might break into different ecoregions. And then just as a for example, we looked specifically at bivalves, these small clams that live offshore, and found that their communities are structured by the winter storm wave base, so how deep the waves from the winter storm penetrate. And so that can give us some ideas of which species might be expected to change if we change the wave environment. Then, as I mentioned, in 2013, there was the proposal for the wind site offshore Coos Bay. And so in the summer of 2014, again, we did multi-beam, we did backscatter, we did video sled surveys, and then we did box core surveys at that site and all along the coast to further characterize the Oregon shelf and down the slope. And then as interest in wave energy, or wind energy rather, moved south into California, a consortium of federal agencies was developed, and they called themselves the EXPRESS Project, Expanding Pacific Research and Exploration of Submerged Seabeds, which that isn't on my slide, EXPRESS, and really did many days at sea using multi-beam, using video sled surveys, using grab surveys. So I would say, like, California and Oregon seafloor is exceptionally well characterized now because of the decades-long interest in offshore renewables and prepping for those potential deployments. Moving into some of the more oceanographic changes that could affect benthic communities. A paper came out in 2023 that was a project that was worked on by a number of different agencies, DOE, NOAA, National Labs, Integral Consulting, modeling changes in upwelling induced by offshore wind farm development. And so modeling predicted that a floating offshore wind farm array of 150 to 500 turbines could reduce downstream wind speeds by 10%. Numerical models indicated this could reduce upwelling speeds by up to 18%, but it's important to put that in context that the natural variability in upwelling is about 27%. And so here is a figure from that paper. On the left is baseline upwelling index, which is an index from 0 to 1, and then when the turbines were in place at the Humboldt Bay in the north and the Morro Bay region in the south, potential changes to upwelling. And you can see that the Humboldt Bay installation modeled changes are much less than the potential changes in the Morro Bay region. We also have questions about underwater sound. I saw that Joe Haxel joined, and so Joe, I'm going to show one of your figures. So questions about this could be referred to Joe. But the underwater sound, can happen at many phases. Here is a timeline for wind farms, but this would be true of wave or tidal as well. Noise can happen during the surveying period, the construction period, the operations, and the decommissioning. The expected magnitudes and frequencies from sound during surveying and construction are well characterized. So the kinds of surveys that they are going to do before installation of a wind or a wave project are the same kinds of surveys that we've been carrying out for decades for all sorts of other seafloor questions, oil and gas, fisheries. So those are really well characterized. The construction, really well characterized. We know what vessels sound like. We know what pile driving sounds like. It's the operations phase. So either noise from the devices or the mooring systems are what are less well characterized. This study from 2003 is one of these that kind of seems like, well, of course, thanks for writing a paper about it. But they found that the occurrence of mooring related sound scaled with wind speeds. So as it got windier, the moorings made more noise. So that makes sense to me. And what remains an open question is whether the mooring noise for any US West Coast installations of platforms for wind energy devices or of wave energy devices will exceed regulatory thresholds. But it is something that we've been actively researching. And so at our PacWave North site, where we deployed that 1/7 scale buoy, we were listening to the site and the deployment. And so this is what noise data looks like. And so we can look at the noise data. Experts like Joe, who know what they're looking at, can extract the patterns that they see from ship noise and from marine mammals, and then look at the signals that are left and see if those appear to be from the device or from the mooring system. We've also been looking at fish and crab response to noise. And so there was in 2021, there was a survey mapping the Cascadia subduction zone with a 36 airgun array. And so we took advantage of that survey to make some observations of what black rockfish, China rockfish, lingcod, and Dungeness crabs did when this large noise disturbance went by. And of course, a lot of data came out of this project, but just as a for example, the black rockfish here, before the survey vessel passed, were distributed more broadly through the Redfish Rocks Marine Reserve where we did the project. As the survey vessel passed, they all clustered around the rocks that were in the middle of the marine reserve because they are rockfish. And then after passage of the survey vessel, they started spreading back out. So they did definitely respond to the noise event, but seem to recover and return back to their normal behavior after the event. Another potential impact to the benthos are the electromagnetic fields from underwater cables. We have hundreds of underwater cables transversing the seafloor. Every oil platform that's deployed has an underwater cable out to it. But in recent years, we've been engaging in more and more research about the potential effects of these. So while the electricity that is going through the cable is shielded, and shielded effectively, it has to be. We don't, for example, we did not accept delivery of the cables until it was demonstrated that there was no leakage of the electric fields from the cables. There is a magnetic field that radiates. That magnetic field can interact with the local geomagnetic field and also induces secondary electric fields as an object moves through the electrically conductive seawater. So as electricity is conducted through high voltage cables, you get small magnetic field artifacts and then induced electric field artifacts. So one of my favorite studies is one that was conducted by researchers down at UCSB. This was a really intensive study, but really excellent. So they took one of the cables that was going out to one of the oil platforms off Santa Barbara and deployed lots and lots of modified crab pots. So this crab pot has two chambers, a chamber on either end, a chamber in the middle, and then a corridor that either crosses the cable or does not cross the cable. They collected hundreds and hundreds of crabs, dropped them into the middle chamber, and then looked to see if they were willing or unwilling to cross the cable to get to bait on either side. What we've got here in the middle panel are the measured magnetic field strengths over the cable. They were, of course, higher in the unburied areas. But the crabs did not care about crossing the cable for bait. Crabs really like bait. They'll pretty much pursue bait over anything. And so they did not find any effect of the cable in the crab's interest in pursuing the bait. Here at Hatfield, we set up this big 6-foot tank, put a cable underneath to look at crab and skate responses. Oh, I thought that video was going to play, but it's not going to. And so we use video analysis and machine learning so that skate, the computer, the AI has put a number of dots on the skate and can track it throughout the tank to look at its position and its velocity in a given moment. And so we suggested them in the tank without the cable turned on, either with alternating current running or DC current running. And what you can see is that the big skates, they just go all around the perimeter. There's doesn't appear to be any attraction to the center of the tank, which would indicate they're attracted to the cable. They are not absent from the center, the midline of the tank, and the long nose skate as well. We think they detected it. Under AC, the big skates increased their velocity a little bit, and under DC, they decreased their velocity. So having some sort of reaction. The long nose skates decreased velocity under both conditions, but again, the spatial use of either did not change with the EMF exposure. In terms of the Dungeness crab and the red rock crab that we tested, they did shift their position in the tank, but not any sort of detectable attraction or avoidance. So you can see the Dungeness crab under the control conditions preferred the northwest side of the tank, and then when we turned the cable on, they moved to the south. And then the red rock crab They preferred the southwest portion of the tank, and then when we turned the cable on, they moved to the north side of the tank. But some of them liked to sit on the midline, some of them preferred to sit on the perimeter. And so no statistically detectable attraction or repulsion. So those are all lab studies or proxies, but we are really excited to start our PacWave South test site. Like I said, we finally laid the cables last fall, and we are hopeful to get devices in the water probably starting next summer. We have already been doing surveys of benthic invertebrates and sediment grabs, flatfish trawls, deploying Dungeness crab pots, surveying marine mammals and birds, deploying the hydrophones, mapping the electromagnetic fields, doing seafloor videos. I don't think there's any site in the ocean that's had more years of baseline in anticipation of an impact because we've worked so long to permit this project. And so we have an enormous amount of baseline data, and excited to launch our test site and perhaps survey potential effects. And I see a lot of questions have come in, and so we'll see how much time we have to answer them, but there is my contact information. Feel free to have any follow-up questions.
Awesome. Thank you, Sarah. Yeah, it's sparking lots of robust discussion in the chat. Please feel free to continue adding questions and or raise your hand. One of the questions that you touched on a little bit is just with this change in energy, you talked about upwelling. Are there other impacts from that in terms of transfer currents or, for example, impacts on juvenile fauna that have been explored?
Good question. So we have done over the years various modeling studies. Okay, so we've got this. So some people may know we've got this great wave basin, the Hinsdale Wave Lab at Oregon State University, where we can put scaled models in, we can put little arrays in, and we can make measurements of the changes in the scaled dynamics, in a wave basin, which is pretty realistic, and then try to mathematically scale up to what might happen in the environment. And there will be, near field reductions in wave energy or tidal energy. I mean, that's the point, right? But a lot of the modeling research has been, okay, well, how can we position devices in arrays so that the resource can recover, in between the devices, so that enough energy passes between them so that downstream it's mostly recovered, and overall maybe we're only having a 5 or 10% impact. The models are powerful, the models are good, but now it's time to put some devices out there and make some measurements and ground truth those models at scale and see how it plays out.
Wonderful. Agreed. It's nice to have that iterative relationship between the model and the monitoring. And as you said, that baseline that you all have is pretty amazing. Some of the other questions here is just about the potential for increase in oil spill risk and how that gets factored into some of the considerations, I think particularly given placement being considered in Salish Sea.
Yeah, so, anytime you're going to have increased ship traffic, there is the potential for, leakages or spills associated with the ships. There will be, depending on the style of the device, various volumes of hydraulic fluid that might be in the devices. I think it is a matter of scale. If the alternative is traditional oil and gas, then the volumes for potential spillage from hydraulic fluid are far less than some other source of energy and its spillage of hydrocarbons. But it is certainly something that is taken into account, is part of the environmental assessment. So like for the PackWave project, you've got your environmental impact statement, all of the work that goes into your license application. And then of course there's monitoring and mitigation, and then safety protocols for things like spills or noise, this, that, and the other. So that's why the permitting takes so long. It's also one of the main reasons, a major reason to have a test site like PackWave is the burden on developers to demonstrate a project if they have to go through their own permitting is really high. Here, we've got something where we have a team of experts who went through the permitting process. No matter what developer is in there, the same environmental monitoring studies will be done, the same safety protocols are in place, the same people are doing the work, certifying the device. And so lower cost for the developer because they don't have to do all that themselves or contract it out, and better outcomes because of the consistency of process.
Absolutely. The acceleration that can come out of these sorts of test centers is really impressive around technology innovation. One of the other questions that we have is just around knowing that for particularly kind of smaller fish, that the changes in flow rate can kind of entrain them, and wondering if there are any studies about tidal turbine cavitation and impacts.
There are. I am not an expert in that as a benthic ecologist, mostly focused on wave energy. But the University of Washington team, many studies in the flume tanks up at UW, many observations of those small scale tests deployed off SQUIM. And so I would encourage you, if you haven't, to invite someone from UW who's more of a tidal expert to do a roundtable.
Absolutely. This is why we need a range of expertise in all of the work that we are doing. One of the other questions was also just in following up on the noise that you talked about, and whether or not that analysis is kind of looking at cumulative impacts of noise, or if a lot of the thresholds are kind of more individualized in terms of how those decisions are made. And on a related note, there was a question about if there are opportunities in the way these systems are designed for some biomimicry that kind of mitigates sound impacts more broadly and potentially creates habitat.
Oh, that was a lot in that question. So starting from the end, I think researchers like me and also developers are excited about the potential for developing devices that can actually enhance ecosystems, have some sort of biomimicry, but also at the moment the industry is focused on efficiency and survival because they are at earlier stages of development. And so a lot of interest in talking about anchoring systems that actually provide more attractive habitat than just a concrete rectangle. But I think that's a down the road thing. The noise, so there are some published thresholds for noise for marine mammal harassment and injury, and so those are what we start with. But the regulatory space is evolving as we get more data on what devices sound like, what mooring systems sound like, constantly taking that in, thinking about developing international standards. There has been some feedback. So we, like I said, the Columbia Power Technologies, they deployed a 1/7 scale device off Newport. They also deployed a much smaller scale device in Lake Washington, a couple other demonstration deployments. All of those we've had hydrophones out, and one element of their device, of it going back and forth, there were stoppers, and the device was hitting the stoppers, and it was kind of loud. And so now the device doesn't have those stoppers, and they've actually figured out it's quieter and it's more efficient. And so that's a great feedback between the monitoring and the device developer being like, this seems like a problem. Oh, we fixed the problem, and it turns out it's even better for the energy generation. So I like to tell that success story.
I love when it works out that way.
Yeah.
Yeah. I was gonna say we'll do one last question. And then just to note that there's been a lot of chat about the forthcoming report from WDFW. When that is made available later this year, I'll try and coordinate and share that out with folks, just since that follows up nicely with this. But for our last question, it's about monitoring the effects on fish or crab larvae, specifically passing through the tidal turbines, and if that's even possible to do that sort of monitoring, given the strength of the currents and the low visibility at the depths that are deployed.
So we have put sonar, upstream and downstream of tidal turbines. The sonar can pick up particles, right, in the water column. We can classify those particles as like probably a larva based on the size, like probably a fish if it looks like it has a swim bladder, in the sonar. There's like a blankness because of the air. So some level of monitoring objects of various size that may pass through the tidal turbine, but I don't believe we're at the point of where we could say, okay, well, that's a fish larva versus a crab larva, and if there were differential effects. So that's with sonar. We also, and by we, pretty much everything tidal is really my colleagues at University of Washington, so this is very much the royal we. Also putting acoustic cameras out, and then my postdoc that did the machine learning for the crabs and the skates and the tanks helped the UW team also with some of the machine learning for the acoustic cameras, trying to train it. Okay, is that a fish? Is that a piece of kelp? Again, based on sort of behavior and whether or not it has a swim bladder. So lots of research and development in trying to figure out how can we make these observations, in a fast-flowing, turbid environment. Yeah.
Yeah, the complex realities of doing a lot of this monitoring and the importance of universities to do that sort of research.
Yeah.
Well, thank you, Sarah. So appreciate the insights from all of this today, and some of the follow-up resources you've mentioned have already garnered support in the chat, so that'll be great. Appreciate everybody taking time today to join, to ask great questions. I hope that you will join us next month when on the 13th, we will be talking about transboundary threats from European green crabs in the Salish Sea. And so that'll be with Tom from DFO, as well as Sean McDonald from UW, and Lily Engel will also touch a little bit actually on larval modeling distribution. So hope to see you all there as well. And thank you for the robust discussion today.
Yeah, thank you, all of you in the audience, for your great questions. You're obviously a really well-informed audience.